so let's get started. Last time I motivated you to think about Calabi-Yau manifold as a possible background of string theory compactification. And so we considered 10-dimensional space and then compactified it for even-dimensional compact manifold times flat space. And the condition is that we want this configuration of, so for simplicity we were considering type 2A or B string theory and consider supergravity limit. And then there the variation of the gravitino was covariant derivative of supersymmetry transformation. So supersymmetry requires that this is going to be 0. And integrability requires that these commute. And this gives rise to condition on the holonomy of the manifold. And depending on the holonomy, you have different number of supersymmetry being preserved. And so we discussed the Berger's classification of irreducible holonomy to classify what and how many of supersymmetry being preserved for particular configuration. Okay, and Calabi-Yau is important class of such compactification, which preserves number of supersymmetry, specifically according to this Berger's classification. In the case of Calabi-Yau, so the number of solutions to this equation, n plus minus, where plus and minus refers to the chirality. When n is odd, n plus and n minus is equal to 1, 1. And when n is even, n plus and n minus is 2, 0. Okay, and so according to Berger's table, this corresponds to the situation where SO2n holonomy. So generically, if you have a Riemannian manifold, holonomy is SO2n. But you can have a complex structure, and if you have a complex structure, and if the metric is compatible with that complex structure, you have a Kahler manifold. And this restricts the holonomy to U of 2n. But that's not enough to have supersymmetry. In order to have supersymmetry, you should further restrict the holonomy, to SUN. SUN. And so this is a condition for Calabi-Yau. Let me write it in a more organized way. So if you have a general Riemannian manifold, then the holonomy group is SO2n, because the Christoffel connection on Riemannian manifold preserves the inner product of tangent bundle. That's the definition. The Christoffel connection is defined by the two conditions. One is that the connection preserves the metric, the inner product in the tangent space, and second is there is no torsion. And this condition implies that the holonomy group of Riemannian manifold is an element. For example, the curvature takes value on in the Lie algebra of SO2n. And but you can put a restriction on it, and you can have Kahler manifold, and there the holonomy is UN. And then you can further put restriction and make it Calabi-Yau, and that restrict the holonomy to SUN. Okay, so this is a case we'll consider for now. I realized that this week actually at the American Institute of Mathematics on the 8th floor of Caltech 4, there is actually a workshop going on about G2 holonomy. So that's another interesting class of manifold in 7 real dimensions, which preserves the very small number of supersymmetry. I think it corresponds to the case where n equals 1. So this is an odd real dimension, 7-dimensional manifold. So there is no left and right chirality, and the G2 manifold preserves the very minimum number of supersymmetry. And 7 is an interesting dimension because if you start from 11-dimensional supergravity and compactify it on G2 manifold, it gives rise to 4-dimensional theory with n equals 1 supersymmetry. So that's another interesting class of manifold. It's more mysterious than this Calabi-Yau manifold. For example, the structure of the moduli space is not well understood. So I wish I could tell you more about G2 manifold, but the mathematics is right now still limited compared to Calabi-Yau. So I'll be discussing Calabi-Yau. I hope there will be a progress on G2 manifold this week, for example. But that's an ongoing project in math. So today I'll talk about Calabi-Yau. So let's go back and discuss a little bit more detail about Calabi-Yau manifold. Okay. So first of all, what is Calabi-Yau manifold? Well, first of all, it's a complex manifold. By the way, this is not a course on geometric method in physics. So I can spend whole quarter discussing all these things. Some of which I have done in my course on modern geometric method in physics 229, and I have actually put some link to my YouTube playlist and also sets of lecture notes, written lecture notes at the campus site. So if you're interested in learning more about it, I recommend you to take a look at that. Okay? So I'll just give a brief summary of what I did in this set of lectures. So complex manifold basically means that one can define a holomorphic coordinate. On the manifold. So that means that, well, you know what manifold means, right? So you have a coordinate chart, a coordinate patch in each neighborhood of point. And then, but they are set up so that they are open set, and this coordinate chart overlaps with each other and covers the entire manifold. And then you have well-defined transition function between those coordinates. And if you just have a Riemannian manifold, you have a set of real coordinates, and transition function is supposed to be differentiable. So that's sort of a definition of differentiable manifold, and the Riemannian manifold requires metric defined on it, which transforms covariant. Now, holomorphic coordinate means that you can actually have a coordinate, holomorphic coordinate z and w, so that the transformation from z to w is holomorphic. Okay, so over here, the transformation from z to w must be holomorphic. So that's the definition. not all differentiable manifolds are complex manifolds. There is a compatibility condition for this. So even if the manifold is even dimension, it's not always the case that you can do this. The manifold requires some particular condition, which I discussed in my lecture. The Kahler is a special case of complex manifold. The restriction okay, and the restriction about the form on metric. Okay, and the restriction is that holomorphic component and totally anti-holomorphic component are 0, and you only have this mixed component. And if you just have this condition, or with this not being 0, then it's called Hermitian. But Kahler means that there is some locally defined function k, so that the metric can be written in this way. And this k is called Kahler potential. Okay, and so Kahler potential is defined, well-defined scalar function on each coordinate patch. So within each coordinate patch, it transforms like tensor like this. But this scalar potential cannot be globally defined scalar function, because if it is, then for example, if you calculate the volume or area of any compact surface, that would vanish, and that would be contradiction. So that means that it's inevitable that when you change the coordinate patch, k is not necessarily invariant. So in general, what happens is that if you go from z coordinate, if you go from u1 to u2, for example, in this overlapping region, k z w z bar. So in general, on this coordinate patch u1, k is a function of z and z bar, and then on this coordinate patch, k is a function on w and w, but they are related to each other by some addition of holomorphic, totally holomorphic function and totally anti-holomorphic function. Okay, so they can differ in this way, but the things that you can add to it should be totally holomorphic or anti-holomorphic, so that del bar cancels this. So that if you take del bar, you have a well-defined tensor field, which is a metric. Okay, so this is often called Kahler transformation. So the Kahler form is therefore not quite invariant, but transforms in this way. This actually give rise to some additional structure. So for example, this means that if you exponentiate k, the under coordinate transformation is transformed into e to the k w bar, but it differs from the original one by multiplication of some holomorphic and anti-holomorphic factor, like this. Right? So this statement is, if you exponentiate it, it becomes like that. So this means that actually there is for each Kahler manifold, there is some kind of line bundle, namely complex one-dimensional vector bundle, for which this is a metric. So you can think, so this implies that e to the k is actually a metric of some line bundle. Where this holomorphic function f, it's a holomorphic line bundle in the sense that if you have a line bundle, then if you change the coordinate patch, there is a coordinate transformation on the fiber, which is one-dimensional complex vector space. And this F gives you holomorphic coordinate transformation of this line bundle. Okay, so there is a natural line bundle associated to Kahler manifold. So we went from complex manifold to Kahler manifold, and then Calabi-Yau. So this corresponds to the condition that the holonomy is UN. But then Calabi-Yau restricts the condition to SUN, and that requires a rich curvature to be equal to 0. So the reason for this reduction was explained in the last lecture, so you can look it up on the YouTube page. Okay? So, and then, but for Kahler manifold, there is a beautiful fact that rich curvature can be written as log of determinant of G, the metric. So therefore, this condition implies that the log of determinant of G is some holomorphic function and anti-holomorphic function. Okay, and so this means that there is a holomorphic in zero form omega. In zero form means that it is rank n tensor, totally unsymmetric with only holomorphic indices, such that determinant of G can be written as omega z times omega bar of z bar. So this is holomorphic depends only on z. The anti-holomorphic depends on z bar. So therefore, metric in general is a function of both z and z bar, but the condition is that if you take determinant, it factorizes. The holomorphic dependence and anti-holomorphic dependence factorizes. Okay. So this means that if you have Calabi-Yau, then there is a holomorphic in zero form. So it was a conjecture of Calabi that the converse is true, and it was proven by Yau. That if you have a holomorphic in zero form, then and also everywhere non-vanishing, then the even path is true. Now this condition is equivalent to say that the first Chern class of this manifold is equal to Z. So you can also say it's a Kahler manifold with vanishing first Chern class. That rich curvature actually is essentially counter first Chern class. So let me give you a few examples and then discuss the family of Calabi-Yau manifold. But let me first give you some examples. So let me start with simple ones. So let's consider the first case where n equals 1. So it's complex one-dimensional. Okay, so what's the simplest one? Well, the simplest one is the complex plane. So this is obviously a Calabi-Yau manifold. So the next simple one is C cross, which is basically which is equal to C with the origin removed. So if you have complex plane, and if you remove origin, so this is 0. So and then then everywhere else is what you consider. So this is a C cross. Okay. You can see that this can be mapped to a cylinder. By the coordinate transformation that Z, so if this is Z, then if you write Z is equal to if you write Z is equal to e to the minus W, well plus W, let's say. So then W goes to, the real part of W goes to minus infinity, correspond to Z goes to 0, and the real part of the W goes to infinity, correspond to Z going to plus infinity. So if you take this to be imaginary part and this to be real part, if you parameterize W in this way, then you can map that to cylinder. Okay, so cylinder is another example. And another example is a torus, which is C divided by the integer shift and also shift by tau times integer, where tau is some complex number with the imaginary part being positive. Okay, so that's an example. And all of these examples, you can have a metric which is dz bar. And with this metric is flat, and so trivially, this is the example of Calabi-Yau manifold. Okay. So let's discuss a little bit about this torus. Okay, so let's first further discuss this torus. So this is C1, divided by Z plus tau Z. So in this for this space, it's convenient to parameterize Z to be called X plus tau of Y. So two coordinate, or maybe yeah, let's do that. And so where X and Y is between 0 and 1, because if X goes from 0 to 1, Z is shifted by integer. If Y goes from 0 to 1, tau is shifted by tau Z. So you have this identification. So you can think of this coordinate X and Y to be periodic with period 1. And tau parameterizes the complex structure. Of the torus. Okay. Now, on this space, we have this what you may call one form. This is a 1-0 form, and this is globally defined. You also have dz wedge dz bar. So I'm using the language of differential form, which again is explained in this playlist that I linked in the canvas. So this is a 1-1 form. This is also globally defined, and this is actually the 1-1 form that is actually naturally related to the metric. So in complex one dimension, this is sort of trivial, but in a general dimension, you can consider this type of 1-1 form, and this is a natural 1-1 form which is closed, and this is called the Kahler form. So for any Kahler manifold, you have this natural 1-1 form which is called the Kahler form, and this is that for the torus. So for Kahler manifold, it's convenient to organize the cohomology, namely the differential form which is closed but cannot be written as something else. So, namely that cohomology, briefly, is a vector space of differential form omega, which satisfies the condition that d omega is equal to 0. The modulo, the condition that you identify two differential form modulo d of something else. D is the exterior derivative. And so in the Riemannian manifold or general differential manifold, you can classify solution to this equation by the degree of differential form, the number of d, dx, dy, dz. But in the case of complex manifold, you can actually refine the notion of cohomology by how many z you have and how many dz bar you have. So you give rise to what's called Hodge number. So Hodge number considered the PQ form. Right? And then basically do the cohomology with respect to that, and you count how many elements of cohomology you have. And it's convenient to organize this in the form of diamond. So in one dimension, in complex one dimension, you have this Hodge diamond. So this is called Hodge diamond. You only have 4 Hodge number in this case because you only have one complex coordinate. So if you have more than one, then you have to antisymmetrize this, so you can do that if P or Q is more than 1. So as you can see, in this case, the Hodge number is 1, 1, 1, 1. So this is a Hodge number of one-dimensional torus. So this is a nice way to characterize the cohomology of the manifold. Okay. So I said that this tau parameterizes the complex structure of torus, but there is also Kahler structure. In fact, Yau's theorem says that if you specify the complex number and Kahler class, then actually the Rich-Kahler metric, namely the Calabi-Yau metric, is uniquely specified. So in the case of torus, as I said, complex structure is specified by tau. And then there is a Kahler class. Which is basically specified by the area of T2, namely the integral of square root of g of T2. And so what is this? Well, so as I wrote over there, the dz, so the metric on this space is dz bar. So you can write this as gij bar dzi dzj bar. Okay, so this is not exterior derivative in the sense of differential form. This is the ordinary notation for the metric. But then there is a Kahler form, which is k, which is g I j bar dzi which dzj bar, and then I put I over here to make it the real true form. And so what is this in this case? Well, so z is equal to x plus tau y, right? So therefore, if you consider dz, which dz bar, this is equal to dx plus tau dy, which dx plus tau bar dy, and so therefore this is equal to tau minus tau bar of dx with dy. Okay, so maybe I should have put minus I here, so that dz bar. So if I put I or minus I over here, then this is equal to twice of imaginary part of tau of dx dy. So you see that if you integrate this, the modular factor of 2, you get essentially imaginary part of tau. Okay, so therefore the volume is like imaginary part of tau, and this imaginary part of tau characterizes. Well, I guess I have to. I didn't say it very well. Actually, in addition to this, yeah, I'm sorry, I messed it up. So actually, so there is an additional possibility that you multiply some positive real number to it. So therefore, this is equal to r times everything. So this is the imaginary part of tau times r. So therefore, there is additional r that parameterizes the size. Excuse me. So the Kahler class is actually parameterized this r, that is this extra factor that control the size of this torus. So you have 3 real parameters. The Kahler class, which gives you the area of T2, and one complex parameter, which describes the complex structure. So Yau's theorem says that if you specify the complex structure and Kahler class, there is a unique Calabi-Yau manifold. And in this simple case, what it means is that if you know R and tau, then there is a unique metric. Okay. So in string theory, it is natural to complexify the Kahler class. So that you write T is equal to IR plus theta, where theta is between 0 and 2 pi. The reason is that in addition to, so if you remember that if you consider type 2 string in the NS sector, there is a metric, the target space metric, that coupled to the worldsheet Lagrangian. But there is also antisymmetric tensor field with relative minus sign that coupled to the B field. And so it's natural to consider this combination as characterizing worldsheet action. Okay. And this actually changes some of the calculations, as we will see. In particular, so what I mean is that when you do the string theory calculation, you use two-dimensional conformal field theory with worldsheet Lagrangian, and we just saw that, therefore, from this description, the kinetic term takes this form. Right, so you can write the kinetic term in this way. And now, this, in the case of torus, for example, this B field if you have constant B field, then this term is actually looks like locally trivial. And the reason is that if you look at the term contains B, you have Bij bar del xi del bar xj bar minus del xi j bar del xi. You can actually write this as a total derivative. You can easily check that this has a form of a total derivative. Like that. So you can write this as a total derivative. So locally it looks like a trivial things. Normally, when you write down the action or Lagrange density, usually you don't care about terms that are total derivatives. But here you care in the case of torus, because x is not a periodic coordinate, but this x and y is supposed to be periodic. So z coordinate, for example, is supposed to be periodic modulo zeta modulo z and tau z bar, tau z. So namely that torus coordinate is modulo integer or tau times integer shift. So this x is actually not a well-defined function. It's defined only modulo integer or tau times integer. So when you try to do that, for example, if the worldsheet is also torus, if we go from one side to the other, z can be shifted by integer amount. And so therefore, integration by parts does not quite work. So there are configurations, there are situations where this B gives rise to non-trivial configuration, non-trivial contribution, and that corresponds to some non-trivial, topological non-trivial configuration of the worldsheet set. And that actually changes some of the calculation, make a difference between string theory calculation and standard point particle calculation. And so we'll see more about that later, but this actually leads to the complexification of Kahler class. So in string theory, it's natural to complexify this coordinate, and so this gives rise to the space. So therefore, the moduli space of string T2 is actually the space of tau for complex structure. And then T, which is, as I said, IR plus theta, where theta parameterizes B field, which is Kahler structure. So we often distinguish Kahler class and Kahler structure. We call Kahler class in the Kahler class in the traditional mathematical sense, and we to construct that with complex the stringy one as Kahler structure. And the reason that we call this is that there is actually natural symmetry between Kahler structure and complex structure by the mirror symmetry, which we may then mention later. And you can think of tau and T as a point in the Narayan moduli space, which is O22 divided by O2 times O2, and then divided by O2 of Z. So this is the simplest case of Narayan moduli space that we discussed at the end of last course. Okay, so that's complex one-dimensional. That's very trivial, but it's good to go through this. So now let's consider complex two-dimensional or real four-dimensional Calabi-Yau manifold. So going up in dimensions. So now two complex dimension. Okay, so actually there are two types. Okay, so one is a trivial extension of what I just did, namely T4. Real 4-dimensional or complex 2-dimensional torus. So 4D torus. Okay, and so you have two coordinates, Z1, Z2, which are both periodic. And in this case, a Hodge diamond is like that. One, two, and H22. So Hodge diamond is like this: 1, 2, 2, 1, 4, 1, 2, 2, and 1. Okay. We can easily see how it works, right? So for example, this 1 corresponds to just constant. These 2 correspond to dz1 or dz2, and this corresponds to dz1 with dz2. Right? And this 4 corresponds to dzi with dzj bar, and there are 2 choices of I and 2 choices of Z, so 2 times 2 is 4. Okay, so you can have this type of Hodge diamond calculation. Okay. The complex moduli space is 4 times 4-dimensional. Complex structure is 4 complex dimension. And that corresponds to the fact that H11 is equal to 4. And we'll discuss more detail about how to parameterize complex structure. But in this case, the dimension of complex structure is related to this H11. And the Kahler class, in the sense of classical mathematics, is also 4 real dimension. And that's also related to the fact that H11 is 4. In this case, actually, it's easy to see that why it is related to H11. Because if you consider Kahler class is Gij bar, dzi with dzj bar. So it is 114. So you can deform this 114 by adding any one of these 4 114. And so therefore there's a natural correspondence between the possibility to deform the Kahler class and the 114, preserving the Calabi-Yau condition. Okay, now, so in string theory, this is complexified in string theory. And the combined moduli space, of course, makes an Ryan moduli space. Okay, so now in general, so as a side remark, in general, if you have torus in d dimension, then you have dd OD times OD divided by OD D. Z, the Narayan moduli space that we discussed in the last talk. Okay, so this is one class of Calabi-Yau manifolds in two complex dimensions. But there's another one which is more interesting, and that's called case 3. And this is in 2 dimension. In complex 2D, this is the only non-flat, so therefore non-trivial Calabi-Yau manifold. Okay. Why it's called K3 is I don't know. There are 2 theories. One is that it's named after 3 mathematicians, Kumar, Kahler, Kahler. But another story is that there is a mountain called K2 in Himalaya. It's hard to climb, and K3 is even harder. So that's another reason that it's called K3. But I don't know exactly which one's true. The Hodge diamond is given by (1, 0, 0, 1, 20, 1, 0, 0, 1). So we can make various observations. First, so this is again a constant. This 0 means that there is no 1, 0, 4, but this also means that there are no isometries. So, for example, torus has lots of isometries. We can translate in torus in 2 different directions, or in T4 there are 4 directions. And this is actually related to this 2, because this means that there's a complex 2-dimensional space of isometries. And so this means that K3 in general has no symmetry. So it's more interesting in that sense. It's not a symmetry. There are no isometries in general K3. That metric and curvature prevents that. Okay, so 1 means that there is a holomorphic to 0 form. And that's a requirement for Calabi-Yau manifold. I showed that if the metric is scalar and reach flat, in n complex dimension, there must be holomorphic n 0 form. So in 2 complex dimensions, you have to have holomorphic 2 0 form. And there is a unique one. That's this one. Okay, and this 20 means that the complex structure moduli space is 20 complex dimension, and the Kahler class, there are 20 Kahler classes. That's what this means. Okay? Classically, in the sense of mathematics, the moduli space of metric is basically spanned by this complex structure and Kahler class. And interestingly, it is also locally O19,3 divided by O19 times O3. So this was proven by Todorov. Okay, it's interesting that it's still a coset space. In the stringy sense, in string theory, the moduli space is the Kahler moduli is complexified, and it becomes O20,4 divided by O20, 04. But in string theory, there are lots of duality symmetries, such as T dualities, etc. And so it's actually that the global structure is such that it's also divided by such generalized duality transformation. So this is the entire structure of the modular space. It's complex, 40-dimensional, and obviously 40 corresponds to 20 plus 20, 20 complex structure and 20 Kahler structure. Okay. This has a beautiful structure. It's an example of quaternionic Kahler manifold. As I mentioned in the last lecture in the context of Kahler's classification, even though it's called quaternionic Kahler, but it's not a Kahler manifold. Even though this is a modular space of Kahler manifold, the modular space itself is not Kahler. It has this structure. Now, the very curious fact. Oh, by the way, so the fact that the modular space has this kind of stringy modular space has this kind of structure was first pointed out by Nati Zyber, and then subsequently verified by many people. But Zyber's argument was very curious. He always had a very clever way to come up with deep mathematical results. And so his idea was that if you compactify type 2 string on K3, then you get some 6-dimensional theory with some supersymmetry. And you also, if you compactify heterotic string on torus, you also get the same type of supergravity theory in 6 dimensions. And in supergravity theory, the supersymmetry actually restricts the type of allowed type of modular space, and that was known. And in heterotic string, the modular space was this. So therefore, he argues that type 2 string, because in the case of a heterotic string, you can use Narayan compactification on T4 to show that this is a modular space. So then he argued that by supersymmetry, then the K3, complexified K3 modular space should also have this structure. And so this was actually a precursor to what's called the string-string duality, which became clear in 1995, where heterotic string theory on T4 is related to type 2 string on K3, which I will discuss later. But this was sort of precursor. Very curiously, the complex modular space of string theory, type 2 string theory, on K3 has a structure which is identical to that of heterotic string on four-dimensional torus. Okay. So the string theory on K3 has lots of interesting structure in physics and mathematics, and so there are a lot of things that we can talk about. But I will defer that to later. And so K3 is first non-trivial example of Calabi-Yau manifold, non-flat example. But it's good to have some, so it comes with a complex 40-dimensional modular space. And at some point in modular space, there is a simple description. For example, in some limit, you can describe it as orbifold that we discussed toward the end of last course. And so there are examples of K3. So one example is orbifold. So for example, you can have a T4, but divide that by some discrete group G, where G can be Z2, which flips the coordinate, etc. Or when so for example, you can flip complex coordinate. There are 4 complex coordinates. You can flip the sign, and then divide that action, and that gives rise to orbifold, which has this kind of structure. If T4 has some particular shape, then you can have a more interesting discrete group to divide the manifold. Okay, so there are other class of things called hypersurface. In projective spaces. So these are another interesting class of construction of K3, which correspond to a particular point on modular space. And these are also very important class of K3 surface because corresponding wall sheet theory in 2 dimensions are exactly solvable. So there is a beautiful thing called the Gepner construction. Which give rise to CFT as exactly solvable model. Okay, so I hope to have a chance to talk about it later. But let me give you an example. So let's start with CP3. Complex, 3-dimensional complex projective space. So what is CP3? Well, you first consider a set of 4 complex coordinates. So 4 flat complex dimensional space, but identify 2 points in the complex space by multiplication of some number. Lambda takes an element of a complex number which is not equal to 0. So you divide this space by this. So then you remove 1 complex dimension, so you get 3 complex dimensional space. So that's CP3, right? So that's a sort of a definition of CP3. And in this space, you can consider a homogeneous function. Pz, and then require of degree d. And then require the condition that this satisfies this equation. Okay, and the reason that it has to be homogeneous is that this equation, so that this equation is well defined on CP3. Because CP3 is defined by identifying 2 points that are related to each other by scaling by complex number. If that satisfies this equation, then even if you can multiply complex number, the same equation is satisfied because it's a homogeneous function. Homogeneous means that if you scale all these coordinates by the same number, this is multiplied by some power of that same number. Degree D means that if you have P of lambda Z, then this is equal to lambda to the D of P of Z, right? So therefore, if this is 0, this is 0. So therefore, this equation is well defined on CP3. So you can consider this equation. Okay? Now, there is actually a simple calculation of differential topology that you can do to figure out what kind of polynomial give rise to Calabi-Yau manifold. So in general, if you consider CP D minus 1, I think, and impose P of Z1. So I think degree D, yes, it's a good degree D. Degree K, I'm sorry. I meant degree K. I messed up the notation. So let's call this as let's call the degree to be K. Degree is K. And let's consider this polynomial or d variable of degree k. So you see that if you have a d variable and identify two sets of variables by rescaling, you get Cp d minus 1. If you impose this condition, then you get d minus 2-dimensional manifold. Now you can calculate the first Chern class of this space. So there is a beautiful formula called the adjunction formula. Which tells you, which helps you to calculate all the Chern classes in this way. Well, in this particular case, it is equal to 1 plus j, well, 1 plus k, I suppose, k of d. Well, j is k are already used, so let me call that as j. Plus 1 k j. Okay, so d is a dimension of related to the Cp, the projective space. So the projective space has dimension d minus 1. There are d variables, and the k is a degree, and then j is I times gi j bar dzi with dzj. Well, okay, so this is a 1-1 form. J is a 1-1 form. So you write it this way, and you expand it in power j. So you get the first term is 1, and the second term is 1-1 form. The third term is 2-2 form, 3-3 form, etc. And each calculates the Chern classes. So that's a sort of formula. So this is a beautiful formula. So in particular, this means that this is equal to 1 plus d minus k of C1 plus etc. So in particular, plus d plus j. So that means that C1 is equal to 0 if and only if d is equal to k. And this gives rise to Calabi-Yau d minus 2 fold, namely that the d minus 2-dimensional Calabi-Yau, because the first Chern class vanishes. Okay, so this means that in general, if you consider Cp d minus 1 and impose one equation where a homogeneous polynomial of degree k vanishes, then if this degree is actually the same as 1 dimension higher than Cp, the projective space, then it actually gives rise to Calabi-Yau manifold. Okay? So for example, so this means that, for example, you can construct K3 as a solution to this equation. So if you consider this equation in complex 3-dimensional projective space, this gives rise to K3. So this is called Kahler K3. So this is a particular point in this moduli space of K3, and it's actually a nice example because orbifold in some sense is some kind of particular singular point in the moduli space, and this one sits right in the middle of this moduli space. But actually it turns out that it's still, the corresponding conformal theory is still completely solvable. We can calculate everything we want to calculate, correlation functions and partial functions, etc. So thanks to the Gepner construction. So this is actually a nice example. Okay, so now I'm going up in dimension. So let's go to complex 3 dimension. And this is one of the most interesting case because this is a case if you compactify type 2 string theory, give rise to n equal to supersymmetric theory in 4 dimension. And as I hope I will discuss in the next week, if you consider heterotic string on Calabi-Yau 3-fold, then give rise to n equal 1 supersymmetric theory in 4 dimension. which contains low energy theory which looks like supersymmetric extension of standard model of particle physics. So that's also an interesting case. Okay, so let's consider Hodge diamond. So the Hodge diamond has this structure. So 1, this is 0, 0. So that means that it's a constant map, constant function. If for connected manifold, H00 is always 1 because there is only one constant function for the connected component. And then you have 0, 0. Again, this 0 means that there is no isometry. Okay, and then you have 0, H11, and 0. So this 0 means that the 2, 0 is 0. But because there is a thing called Hodge duality, which means that these and these are the same. So in general, Hodge duality means that if you have n-dimensional space, HPQ is equal to H of n minus P Q is equal to H of P n minus Q is equal to H of n minus P n minus Q. So Hodge diamond has lots of reflection symmetry. So actually these two zeros are the same thing. And now you have 1 and H 1, 2 and H2, 1 and 1. And this 1 corresponds to the fact that there is unique everywhere non-vanishing holomorphic 304. So this is again required by the Yau theorem. And then you have 0, H22, 0, 0, 0, 1. But because of this reflection symmetry, this is actually 1, 1. Right? And this is actually 1, 2. Because these are the same number. So there are only two non-trivial numbers in Hodge diamond, and others are sort of consequence of what we would expect this to be non-trivial manifold, that there are no isometries and Yau's conditions satisfied. So there are only two numbers, H11 and H12, or H21. So these are the two numbers. And these two numbers has meaning to it. So this is actually the dimension of Kahler moduli space. Complex dimension of Kahler moduli space, and this is the dimension of complex structure moduli space. Okay, so in 3 dimensions, the dimension of complex structure and Kahler class are in general different. And another important quantity is Euler number, so that's the alternative sum of Hodge diamond. Okay, but because 3 is an odd number, so if you can calculate chi, these and these and these and these cancels out, and then these add up. So you get twice of H11 minus H21. So therefore, chi is essentially the difference between the number of complex moduli and Kahler moduli. Okay. So in general, for Calabi-Yau n-fold, H11 corresponds to Kahler class, Kahler structure, and then n minus 1 1 correspond to complex structure. Okay? So that's Calabi-Yau 3, 4. And then we can go on to higher dimensional Calabi-Yau manifold. Okay, so I have already told you that for K3, this gives rise to interesting class of examples, and but the condition was D equal K. So therefore, this naturally gives rise to an example. This naturally gives rise to the example of Calabi-Yau threefold, and the famous example is quick. Calabi-Yau threefold, which is given by z1 to the fifth plus z2 to the fifth plus z3 to the fifth plus z4 to the fifth plus z5 to the fifth is equal to 0 in CP4. Okay, so this again corresponds to the case when D is K is equal to 5. And this satisfies the Calabi-Yau condition, but now it's a hyperplane in CP4, so it's Calabi-Yau threefold. Okay, and this is exactly solvable by Gepner model, and so we can calculate C, which is 1 plus j to the 5 divided by 1 plus 5j, and so this is equal to 1 plus 10 j2 minus 40 j3. So we have to actually understand the normalization of j3, and so we have to calculate. So we can, for example, so this one, for example, is C3, and so this is interesting because this is C3. So therefore, so if you calculate the integral of C3, then this is chi, right? And but so to calculate this, we have to calculate J3. Okay. Actually, there's actually a nice trick that you can use, which is that instead of calculating J3 integral of J3 on K3, we can actually bring this back up to the original CP4. So you can calculate CP4 by J3 to the J to the cube, which 5 of J, and this 5 of J corresponds to this 5. And so this actually, since integral of J on CP4 is normalized to be 1, so this is actually 5. So 5 times 40. So from that, we conclude that we can calculate chi to be minus 200. So you can count the difference between H11 and H21 for quintic Calabi-Yau in this way. Quintic is a very important class of Calabi-Yau because it is actually solvable, so we can actually calculate correlation function. And it gave rise to the first non-trivial example of mirror pair of Calabi-Yau manifold that I will discuss later. Okay, so I only have 3 more minutes, I think. And so what I would like to do next is actually give you some more detail about the structure, tell you about the structure of the moduli space of Calabi-Yau. And so this is actually very important for discussion of the Calabi-Yau space. And so let me just begin to discuss it. So what I would like to do is study the moduli space. Of Calabi-Yau. So this is important because if you compactify string theory, then you get the family of low energy effective series, and the moduli space of Calabi-Yau parameterizes this space. So so we want to understand, for example, the complex structure moduli space. Of Calabi-Yau, so which I denote by M of C. And clearly, this is related to the holomorphic N0 form. So let's restrict ourselves for simplicity to 3, although we can discuss it more generally. So we consider holomorphic 3 form omega. So we're going to utilize this holomorphic 3 form to define the metric and discuss a structure. It turns out that the MC, so I'm going to give you some preview. So it turns out the MC itself is a Kahler manifold. It's a Kahler manifold, so therefore, but it's not a Calabi-Yau itself, it's a different manifold. Just like, for example, in the case of a torus, the moduli space is an array moduli space which is called anionic Kahler manifold. Moduli space of Calabi-Yau is a Kahler manifold, but it's not rich flat. The metric has a particular structure, and it's closely related to the holomorphic 3 form in the sense that actually if you have Kahler manifold, you have a Kahler class. And this Kahler class is related to the integral of holomorphic 3 form on the Calabi-Yau manifold. Okay, so we'll discuss those structures in the next lecture and then uncover some of the geometric features of the moduli space. So we'll do that in the next lecture. Now, I want to ask you about the schedule. So I am going to miss a few classes because of my travel. So I would like to do some makeup class. So I would like to ask whether either one of these is possible. So currently the class is Monday and Wednesday, 9 to 10:30, right? Would either Thursday, 9 to 10:30, or Friday, 9 to 10:30, work for you? Is there anybody for whom either of these are inconvenient, like conflict of classes? If there are, could you raise your hand? If not, can I choose either one of these? If you don't hesitate, if you have any conflict, you let me know.